So welcome back. Last time we talked about electric potential energy, and electric charges. And really that should effectively give us everything we needed to solve a lot of these problems. However, figuring out exactly how a charge is going to move can actually be fairly complicated because while the electric potential energy and the electric potential are scalars, the velocity and the position, the displacement, and everything that electric charge is going to move through is a vector. So doing the calculations and figuring out how these things are going to actually move is fairly complex. Well, fortunately, there is an easier way. In 1831, there was a laboratory scientist by the name of Michael Faraday. He was probably the best laboratory experimenter that has ever existed, but he never went to school. He had no formal education, and he really wasn't terribly good at math. And so he was really interested and fascinated in these electric fields, electric charges, and all this other sort of thing. And so he wanted to come up with some way that he could experiment with it that didn't require math. Now, I'm sure a lot of you might be interested in finding a way to do these without math as well. So he invented this concept called the electric field. So that's what we're going to look at right now. Is for this video, we're just going to introduce the concept of electric fields, how we draw them, how we make these. And you can think of it as a map. We talked about this last time when we talked about gravity, how, if this is the Earth, and then I could say, okay, everything at this distance from the Earth is going to have this amount of electric potential. So if I drop a mass, or I'm sorry, gravitational potential. So if I drop a mass here, I'm going to have that much gravitational potential energy. Well, we can do exactly the same thing with an electric potential. And so now that map then becomes the electric field. So what we'll do is first we'll learn Faraday's rules for how to draw these maps, how to draw these electric fields. And then we'll come up with some mathematical expressions to show how these things are related to the electric potential and then eventually the electric force. All right, let's get started. All right, so again, here are your notes. This is the textbook, and you should be taking a look at this. But what I want to show you here are some of these maps. You can actually see these fields yourself. Now, the easiest way to see these are with magnets. And you may have done this experiment before where you've got a magnet and you sprinkle some iron filings on there. The iron filings will align themselves to the magnetic field. So let's zoom in on this one right here. Here we have just kind of a standard bar magnet. It's got a north pole and a south pole. And you see that those filings arrange themselves like this. So it goes from the north to the south. And then these over here kind of just go off into infinity with this. So what this does is it tells how, a piece of metal or anything that could be magnetic will actually fall and move. If I have some sort of tiny little magnet, I can see how that's going to go. We can also take a look at this one. Here we've taken the two north poles and put them together. And as you see in between, there's no magnetic field. There's no magnetic field at all. Everything that tries to move this way is going to get repelled by that other end. And it's going to come flying out on this other side, maybe get attracted to the south end of the magnet with that. So electric fields do exactly the same thing. These are some plastic fibers that are floating in a solution with two electrically charged balls that you see here. And since these two have the same sign, they're the same charge, then you can see that we get a pattern that looks very similar to what we saw with the magnet up here. It's a little harder to see the electric field. And that's why the magnetic field is probably a better illustration, but it's still there and it's still basically the same thing. So in order to learn how to do these, we're going to have to learn Faraday's rules for drawing these field lines. So let's zoom in on this right here. I'm actually just going to delete this. There we go. So these field lines are vectors, and we need them to be vectors. The reason for that is because if I have an electric charge and I drop it, I want to know in which direction it's going to move, not just how fast, but which direction. And so that necessarily means that it's going to be a vector. So Faraday's rules are the field lines are vectors that point away from a positive charge and towards a negative charge. So I've got in parentheses here, one of the best ways to think about that when you're trying to draw these fields and kind of get it in your mind. It is true that in general, it is only the electrons that are moving, which are negatively charged. But if you want to remember how to draw the field lines, the vector points in the direction that a positive charge is going to move. So think about it in terms of, well, okay, and we're going to sketch this down at the bottom, and hopefully this app will do a little bit better than the other. So let's say that I've got a positively charged thing, a ball of some sort, and I drop a little tiny positive charge right here. Well, how's it going to move? Well, they're going to repel each other, so it's going to move straight out, just like that. If I have one up here, then it's going to move straight out. Let's erase these. Now, if I have a positive charge and a negative charge that we're going to look at in just a minute, I can launch out from this positive charge, but now it's being attracted towards the negative charge. So it's not just moving away from the positive charge, it's also moving towards the negative charge. Same thing is happening here. And then if I have one right here, it's going to go straight. So you see that positive charge is mapping out those field lines. So it's going to give us that kind of effect. If I have a positive charge here, I might have a field line that looks like this, but which way is it going to come in? Is it going to come in this way, or is it going to go out this way? Well, it's positive, so it's going to get attracted. So that one has to be like this. And you see that the rest of the arrows are coming in the same direction. How about over here? It's a positive charge. So is it going to attract or is it going to repel? Well, it's going to repel, so it's going to come out this way. And it's going to start moving out. And I could fill in these if I want. And you can, the number of these lines, though, tells us something about the strength of the charge. So the way Faraday defined it is the number of field lines is proportional to the amount of charge. So right now, I've got 1 plus 1, let's call it a microcoulomb. So plus 1 microcoulomb and minus 1 microcoulomb. So I need to have the same number of field lines coming out of the positive charge as I have going into the negative charge. Now, if I have, let's say I have a positive 2, so let's say I've got 2 positive charges here. That means I need to have twice as many field lines coming into here as would be coming into here. Well, okay, that means if I've got 6, I've got to have 6 more field lines coming out of here, but they cannot land on the negative charge. So field lines always connect the positive to the negative charges, and here's where we can deal with that. If there are any leftover charges, they go to infinity if it's positive, or come in from infinity for negative. So what I can do then is I can say, okay, I've got additional ones, 2, 3, 4, 5, 6, that leave from the positive charge that don't make it to the negative charge. Let's see if that makes sense. If I drop my little positive test charge right here, this is much stronger than this. So it's going to get a bigger kick, and it's going to be a lot further away. So this is going to be pushing out a lot harder than this one's pulling in. And so over time, it's going to escape off to infinity. On the other hand, if I have one over here, this is pushing really hard, but it's headed straight towards it. So it's going to get attracted. It's going to come straight in that way. Right? So this is one way that we can make sure that we have a good representation of what's going on. So the other thing tells us the closer the field lines are together, the stronger the electric force. Now, I'm going to, again, erase this right quick, and let's just talk about a single charge here for the moment. So let's say that I've got a positive charge here. Well, my field lines, remember, should look something like this. Okay, let's switch to red. Out here, those field lines are farther apart than they are right here. So that tells us that the electric force is going to be much stronger here than it is out here. And that's going to be true in all cases. The closer these lines are together, the closer the field lines are together, not the dashed lines, the closer the field lines are together, the stronger the force is. So this is a pretty useful model that we can use. Oops, don't want the ruler there, I'm not the eraser. Okay. So let's take a look at our old friend, the capacitor here. Now, what I want you to do is I want you to stop the video for just a second, and I want you to see if you can draw the field lines. Now, we're going to assume that we say that there's a negative charge on the left plate and a positive charge on the right plate, and they're equal. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. Pause the video and draw what you think these field lines should look like. Remember, you can use a positive test charge and see how that test charge is moving away from or towards each of the plates. Take a minute and do that. Okay, so to start off with, by applying Faraday's rules for the drawing, I've got the same number of charges on each side. So I must have the same number of lines leaving the positive plate as I do entering the negative plate. Now, it says, does the field of the capacitor have an X component? Well, if we define, this way to be X and this way to be Y and then this way to be Z, kind of coming out of the page, you should see that its electric field is going to have to be in this direction. If I had one coming out in the Y direction, for example, it would have to find some way to land here. So it would have to kind of come over here, right? Well, all right, so now it's got an X and a Y component. But what if I made these things infinitely long? If they're infinitely long, then this never ends. And so my only choices are to come out this way or to come out this way. And I'm not drawing my arrows in the correct direction. But I keep hitting the ruler instead of the eraser. These lines, though, would never land on the positive charge. So therefore, if I think about dropping my positive test charge here, it can only go this way. I can't have anything going here. If this is an infinite plate, it's going to move, it would move off to infinity, but I have to have the same number of lines hitting each one of them. So the field between the plates must look something like this. Now, I absolutely can have a field going out here, but I'm not really interested in that because that's not how we're going to be moving in between. Now, in reality, just like we said, you're actually going to have something that looks like this on the edges. So we make a very small error by assuming that this is an infinite plate. If the plates are very close together compared to their length, then that error that we make is so small, you're not really going to detect it. And so in the end, then, we're not going to have to worry about this one unless it's a picture kind of like what we have here, where they're very far apart and they're very short plates. So try to visualize that as being infinite. So does the electric field of the capacitor have an X component? Well, yes, it does. Does the electric field of the capacitor have a Y component? Not if they're infinite. Not if they're infinite. So even if I'm looking at things going out here, they're just going to go straight out. Does it have a Z component? Well, no, for the same reason. Now, remember, the magnitude of the electric field is going to depend upon how close those field lines are, because the field and the force are going to be directly proportional. So does that change with position? Do these lines ever change how far apart they are? No. So it's going to be a constant no matter what I do. So is the electric field constant? Yes, it must be, because it doesn't change. All right? So this is a really useful kind of method for doing this. So drawing pictures is all well and good. So, for example, I could, if I zoom in here, uncheck my selection box here. If I drop any kind of charge in this area, I know exactly how it's going to move. If I have a negative charge, it's going to move against the field lines, just like that. And if you think about it, that makes sense, right? It's going to get repelled by this negative charge. So if I have a little electron here, he's actually going to move that way, because he's getting repelled. But either way, he's still going to follow these field lines. So he's always going to move straight across. And that's what makes this capacitor a fairly useful teaching device, because the fields are actually really nice and simple. It's only in one dimension. All right, now we need some kind of mathematical way of representing the electric field. So let's bring this next microtask out. So go ahead and flip over to that next page. Let's get some practice drawing. And then we're going to use what we learned here to come up with a mathematical way. So what I want you to do now is stop the video, see if you can actually draw all of these electric fields that you see here. Stop the video, really important, and let's do that now. Okay, did you pause the video? If not, you should feel very, very guilty and you're not learning. Okay, so we've already talked about this one. We know how this one works. It's going to leave the positive charge and it's going to land on the negative charge. So the simplest line is going to be right here. Let's see, I don't actually want to draw a line. I just want to freehand it. And then this one is going to go right here. Let's put an arrow on that. And so maybe I'll have something like this and something like this. And then if I want to draw the ones going out here, I can draw those going to infinity, like that. But in most cases, we're going to be interested in what's happening between the charges, like we did with the plates. Okay, now we have the second scenario where we have twice the charge, and we addressed this before, you should have twice as many field lines leaving that 2Q, where Q is the charge, we'll call it 1 microcoulomb, as we do entering here. So I can draw 1, 2, 3, just for now. And then I would have an additional 1, 2, and 3. You see how that works? Now, this is technically correct. I have 6 lines coming out of the 2Q, the positive 2Q charge, and only 3 coming in. But it's a little misleading because it makes it seem like that there's no electric field out here. So you'll find that in order to be nice and explanatory, you probably want to draw what everything looks like. And all that means is that I need to have 12 lines coming out of here. Well, I've already got 6. So that's 1, 2, 3, 4, 5, 6. And so you can see that the electric field and the electric force are going to be much stronger over in this region simply because the lines are closer together. And that makes sense, right? I've got more charge here, so of course the field line is going to be stronger. Now, we could do the same thing with a negative charge. Remember, the only difference here is I'm going to have twice as many lines landing on the negative charge as I do coming out of here. So let's draw the obvious ones first. So that's going to look like this. Right? And I'm going to be, so I've got 3 leaving here and 3 leaving here. However, again, for the same reason, let's go ahead and put in some charges over here, or some field lines over here, so we can see what that's going to look like. So I've got 6 coming out, and this needs to land on the charge. Here we go. And I've got 6 coming in, but this is 2Q, which means I need to have 12. So I need an additional 6. So that's 1, 2, 3, 4, 5, 6. So it looks very similar to the case that we have above. But remember, if I have a positive charge and I drop that positive charge right here, it's going to go in the direction of the arrow and it's going to be attracted to this. Same with an electron. It's the same idea. It's still going to follow this. It's still going to follow these field lines, but now it's getting repelled. So if I have an electron over here, it's going to move outward, opposite from the direction of the electric field arrow. Would have been nice if Ben Franklin had chosen the other rubber rod to be positive instead of negative, because then I would say, okay, that thing that's actually moving is actually going in the direction of the arrows. Unfortunately, he didn't, and we're stuck with what we got, and that's why we hate Ben Franklin. So if I have any 2 charges of any magnitude here, then we call that a dipole. A dipole means 2. So if I only have 1, then that's a monopole, because mono means 1. So if I have a single positive charge, where are those field lines going to go? Stop and think about that for a minute. Well, we've already drawn a similar case to that. So if I have just a single positive charge here, and it could be Q, 2Q, 10Q, 100Q, whatever it is, then the field lines are simply going to go to infinity, like that. Now think about the single negative charge. You should be able to figure this one out. Right, so all of those are just going to come in from infinity, and so it's going to look basically the same, but the field lines are coming in. Right, so that's the fundamental difference between these monopoles, these electric monopoles. All right, so let's bring the next microtask up over here. All right, so we want to, now that we've kind of drawn some maps, we want to see if we can come up with a mathematical expression for it. So suppose we make the change in position infinitesimally small, right? Now, we defined, if you look in your notes, we defined the electric charge, or the electric field to be how the electric potential varies over a given displacement, right? Over a given displacement. So I could write that then in this way. Let's write it over here so that we write it without the differential. So in general, it's just going to be, that's a delta V divided by delta X. Just like that. Now, you should, hopefully by now you're familiar with how to convert this into a differential. So if I take a very small element, then I could say that my small dE here is going to be equal to dV dx. And of course, these are going to be vectors from here. Okay, now we want to know how this relates to the motion of the test charge. So the change in potential energy is the potential times the test charge, because that's the work that's done. Remember that from the very first part. So again, as always, we're going to call that test charge Q. And let's multiply both sides of this times this. Now, this would be a small change, but the entire electric field then is, we can write it this way, right? We're legal doing this because I've got E equals delta V over delta X. So E is dV dx. So the total change over here after I do all of these. So we're going to multiply both sides, and I get Q times E. Both of these, this is actually a vector. We're going to have to talk about what that does in just a minute. Let's go ahead and make those vectors as well. And that's going to equal to Q times dV dx, where these are vectors as well. Okay, now I cannot integrate this as long as this is here, but if we look, we should see some simplification. What is Q times dV? What is the charge, the test charge, times the electric potential? Well, that's the electric potential energy. So we can say that this is also equal to dUE dx. And the nice thing about that is that that's going to be a scalar. That's how I know that that right there has to be the dot product of it. So this is a little bit simpler for us to work with. Now, if we want to integrate this so that we can get our entire expression, then we have to move that differential over to the other side. So I'm going to have QE is a vector, dx, which is a vector, equals dUE, which is a scalar. Well, this is a scalar, this is a vector, this is a vector. Well, when I multiply two vectors, I have to either use the dot product or the cross product. So if I multiply that right there, then that's going to have to be the dot product because I want a scalar by the time I'm done. So this is a scalar, this is a vector, this is a vector. But when I separate these, that's going to end up being the dot product there. So what we want to say is here, we point out that there's something deep. What's the relationship between the work done and the change in potential energy? Well, hopefully you remember from your previous classes that the work is just the integral of the total change in that energy over the entire path that we take. So this tells me then that the total change in energy is just going to be the integral of all of that. So let's write this, and so we get Q E dot dx, so that's going to make that into a scalar, is going to equal to the integral of dUE, just like that. So this is from UE1 to UE2. Hopefully you've learned in your previous courses to recognize this construction. Anytime you might take the integral of du or d anything, then it's always going to be delta of whatever that quantity is. I'm running out a little bit of space here, so we'll put this off to the side. So I now know that delta UE is going to be equal to the integral from x1 to x2 of QE, which is a vector for now, dotted into dx, just like that. All right, so the next part here asks, what is the mathematical definition of work? And if you don't remember that, go back through your notes from your mechanics classes. So we want it in terms of force and displacement. So we know that F is the integral of the force dotted into that displacement, just like that. All right, so we're going to compare this. Let me scan this. Whoops, we're going to lose that piece there. So if we compare this to what we found here, look at that. This tells us since delta U is also the work, this is the work, then if this is dx, that tells us something very, very interesting. It tells us that the electric force, which is a vector, must simply be equal to Q times the electric field. So this shouldn't be too surprising because we talked about how the whole point of this electric field is to tell me how these charges are going to move. So if I take my test charge, that's Q, and I drop it in my electric field, I now automatically have the force. The vector of the electric field is also the direction, the vector for the electric force. So that's why it's going to move along those lines. So that's pretty darn useful. All right, let's go ahead and get rid of this one. Look on the next page. Let's get rid of all these pieces here. Okay. So let's look at the next page. Now, if we're working in more than one dimension, then we're not, with the parallel plates, it was only in one dimension. It was delta x, and that was fine. If I'm working in multiple dimensions, well, now I have to look at the change in each one of those, the partial derivative in each one of those directions. And that's what this is here. This is called the gradient. And it's pretty easy. This whole thing is going to end up being a scalar, but it's the partial of v with respect to x plus the partial of v with respect to y plus partial of v with respect to z. So that's going to give me, v may be a scalar, but by the time I add in this derivative, I'm going to have these vector signs here. And so my overall gradient then is going to be a vector. So it's the gradient of this scalar. Okay. So the gradient points in the direction of the greatest increase. And I make a note here that you can think of that as going uphill. So the gradient vector arrow always points towards the greatest increase. And so for case of gravitational potential energy, obviously if you're increasing, you're going uphill. And so if you look at a topo map, you can actually see that and you can draw that on there. All right, so now if I were going to write the electric field and the potential, that formula that we just got just a second ago, then I could do that using the gradient symbol rather than just writing partial v partial x. So the total electric field, let's get that single line in there, is the partial v partial x plus partial v partial y plus partial v partial z. I can simply indicate that the electric field then is just the gradient of the electric potential. And that's going to be very useful from a calculus standpoint when we're doing that. Okay, now there is one last wrinkle that we have to deal with. Remember that we talked about how Faraday created these field lines so that it would be in the direction a positive charge would move, right? So as I say here, all of his field lines will go from this positive source charge to a negative source charge. But the electric potential is defined to go from negative to positive. Remember how we had our plates and we had our negative plate over here and our positive plate over here. And so we set that to be 0 to the positive end. So that means that the electric field is always going to have the opposite sign of the electric potential. Okay, that's not a problem. So all we need to do then is just put a minus sign in front of our expression here. So all this means is that, hey, whatever direction your potential is changing, the electric field is actually in the opposite direction from that. Simple as that. Nothing really complicated with it. Okay, so a little bit of math going on with that. There's a lot to take care of there, but go back through it and make sure that it all makes sense to you from there. Okay, now let's look at the last section here. To pull this down where we can see it. Okay, so if we know how the potential is changing, then as we say, we also know how the electric field is changing. So the electric field, remember, is also giving us the electric force. So you remember that force is equal to Q times the electric field. So if I know how the electric field is changing, I also know how the force is changing. So I can also go the other way. I can use the electric field to find an expression for the electric potential, which is often what I want. Remember that voltage is the electric potential between the plates. So we want to start with that first expression that we found. The E is the negative gradient of the potential. And we want to find the potential difference between the plates of that parallel plate capacitor that we've got there. We're going to define the electric field to be E, and as I say here, the separation, the distance between those plates, we're going to call D. Why don't you pause the video and kind of puzzle through that a little bit. I want you to definitely work with that just for a little bit, and then we'll come back and we'll see how it's actually done. So pause the video now. Okay, so let's draw us a quick little sketch here. Let's get my camera back on here. There we go. So we're going to draw a quick little schedule here, or sketch here. So here's my plates. And there, if this is the negative plate and this is the positive plate, then we know our E field is going this way. So that's E, which is a vector. And then this separation, we're going to call D. All right, so starting out, the electric field is the negative gradient of the electric potential. Now, that's going to have a partial x, partial v, partial x, partial v, partial y, partial v, partial z. But remember that we found that the electric field only varies as a function of x here. So the partial with respect to y and z must be 0. So the nice, easy way that we can write this is that it is negative partial v, partial x. And again, that's going to be a scalar there. Oh, I'm sorry, a vector sign there. So starting with that then, let's see if we can come up with an expression. So I'm going to multiply my dx over here because remember, I cannot integrate this unless I have just a single integral in the numerator over here. So I'm going to say that E times dx. Now I've got two vectors here. I'm going to have to think about that in a minute. Is going to equal minus dv, partial v. So this is a scalar. That means that I need a scalar out of this. So ask yourself again, am I going to use the dot product or am I going to use the cross product? Well, I want a scalar, so obviously it's going to have to be the dot product when I'm multiplying it. Okay, so now we're going to integrate both sides. Now notice that E is in the same direction as D. Our dx is going to be our d. So that means that if I write this out, e dx cosine theta is just 1 in that case. And that's going to be pretty convenient. So I'm going to go ahead and write this over here. That's just e dx. E, we decided, was constant. And it's going a distance from dx is going a distance from 0 to d. So since it's constant, I can pull it outside the integral. Integrate both sides here, sorry. And so this tells me that my potential difference, remember that construction right there, my potential difference then is going to be equal to E integral dx from 0 to d. Well, integral of dx is just x, and so this gives me E times d. So my potential difference then is just negative E times d. And that's really handy. So if I want to know what the voltage is between here, remember the voltage is the potential difference between this plate and this plate. It's just minus the electric field times d. So once you draw those field lines, you get the potential difference. So question is asked, is the electric field constant across the capacitor? Yes, that's why we were able to pull it out. So is the electric potential constant across? Yes, it must also be constant because the electric field is constant. Okay, so if the electric field is constant on that past segment, you saw that we pulled it out. But even if it isn't, most of the time we can actually do the integration fairly simply. So for example, if I have just a spherical test charge or a spherical source charge, we'll draw it over here, right? The electric field is not constant in x, is it? But it is constant as I move outward from here. And so I can, if I choose my coordinates correctly, I can still do that integral. I can use the spherical coordinate form of the gradient operator. So once I put it in terms of this gradient, then I can actually convert into different coordinate systems and I can solve these problems really, really easily. So that is a very useful technique. And again, the whole point of this whole discussion is to get you used to seeing how to work with these electric fields. Okay. Now, the last thing, anytime we introduce a new concept, we always have to have units for it. We have to come up with what kind of units are it. Is it coulombs? Is it volts? Is it meters, kilometers, whatever? So a very common technique that we use is dimensional analysis. If you haven't used that in your previous classes, well, you're going to be using it now and you're going to be using it pretty much throughout the course. So here's how we do it. We take any equation we want. any equation that's going to define this thing that we're looking for. And then we use that to figure out what our units must be. So, for example, we found that F was Q times E, right? So if I want to know what the units of the electric field are, I can solve this for E. So I get E is going to be the force times Q. Well, what are the SI, System International metric, whatever you want to call it? What are the SI units of force? That's the Newton. And of course, we abbreviate that with an N. What are the SI units of charge? And you have to remember this from the previous lecture. Right, that's going to be the Coulomb. And you'll see that written as a C. I will sometimes write it as a COUL so that it doesn't confuse you with thinking that it's Celsius or something like that. Either one of these are correct. So what must the units of the electric field be in order to keep the units the same? Well, now all I have to do is just divide these. That's going to be Newton divided by Coulomb. So the units of the electric field then, which we'll be using from here on out, is a Newton per Coulomb. Okay, so today we talked about electric fields, mostly as a map, mostly as a way for us to visualize what this is causing these charges to move around and how they're going to behave. And it's a really useful thing that we're going to be wanting to use pretty much throughout the course. But we also need to do some calculations with it. So even though Michael Faraday wasn't very good at math, you are. And so we demonstrated how we can do some very simple integrations with these differential equations to figure out how a mathematical expression for all these things that we're using. That's a technique we're going to be using pretty much throughout the whole course. So if you're at all confused by that, I want you to be sure and make a discussion post and let's talk about it. Or even let's get together live and let's kind of walk through it. So we want you to have that warm fuzzy. We want to make sure that you're like, okay, yeah, I got this. If you're thinking, well, okay, I kind of got this, that's not going to be good enough because you think about it. Well, I've kind of got this. I've kind of got this. I've kind of got, no, I don't got this. Instead, what we want to think is, well, I kind of got this, and you come talk to me, and we're back here. And I kind of got this, and I come back. And I kind of got this, and come back. And that will keep you on the straight line that'll get you through the course and understanding all the material. We'll see you next time.